It's Mr. Rops.
I'm Mrs. Flynn.
And we are here to do a problem with optimization. And so, with this problem, we're given a piece of cardboard with dimensions 6 by 8 centimeters, and 4 squares are cut out. And we're going to find the corners are folded up, and a box with no top is created. So to get a sense what it looks like.
So here's our box, and if we look, we have a length of
This
8.
is 8 here, which is shown by 8.
And then a width of 6.
Which is this distance
And
there.
each one of those red squares are a box taken out. And those for now would just be, we'd call those length X.
Right,
But
so X by X. Okay. And so if we fold these up and get rid of these red squares, we get the box that's over here. And so if I
let's go ahead and just explore a little bit with different sizes of X.
Right. So if I change the size of X, I get different size boxes. I get a really small X, I get a really thin box, or I can make boxes that are really
Tall and skinny.
tall and skinny.
So which one's going to give us the largest volume? That's the main question here.
Right. And so this point G that's over here is tracing out the volume. And so we're looking for a volume that's up around here somewhere to the maximum, which is going to be somewhere around 1. But we have to use calculus to find out that scenario.
And we can do that. We know how to solve for maximums.
Exactly. So here we go. It says make an expression for the volume in terms of X.
All right, so if we have our box, and in our box we have a length of 8,
All right.
and
Here's
we
8.
have little or squares, I guess, cut out.
And these are all X's that have been cut.
So now if we have a new length,
All right.
that total new length would be 8 minus 2x.
And as we know, volume of a box is length times width times height.
All right.
And so this length is simply 8 minus 2x.
Now we have to find the width.
The width, well, if I cut out the corner here, this was the 6, cutting out the x, this would be the width, which is 6 minus the 2x.
So same process.
Same process, 6 minus 2x
Now times it by the height.
is just x. And so
Okay.
here is our volume. Let's multiply this out. So we'll go through, I get 48, let's put it in parentheses, minus 16x minus 12x plus a 4x squared.
I'll multiply it by x.
If we put it all together, and I'll put the 4.
Order of exponents.
All right, I go 4x cubed minus 28x squared plus 48x. And so this is a part completed, an expression for volume of the box in terms of x. So now volume is a function of x, v of x.
All right, part B. Use calculus to find the max volume of the box and the dimensions.
Right. So the maximum, or optimizations, that's first derivative. We want
Yeah.
to find a maximum.
So for the first derivative, we
Differentiate,
Yep.
we get
12x squared minus 56x
plus 48. Okay, so now we just have to, if we want a maximum, we need to make this equal to 0, and we
Yeah.
have to solve that.
That'll solve for our critical points. So if we want to make it easier, we could factor out a 4
A
maybe.
4, that's, okay, we'll put the 4.
Yeah. Just the,
And so it's a 3x squared minus 14x plus 12 equal to 0.
Okay, instead of trying to figure out how to factor that, let's just do this quickly by putting it
Right.
into our graphing calculator.
Which we've already worked ahead. There's our equation, we graph it. And so we have 2 zeros here, one here, one here. Let's find them. I go second, trace my 0. My left bound, 0. Right bound, let's say it's 2. My guess is at 1. And so I get 1.31. So
Okay.
x equals 1.31 to
Okay.
3 significant figures.
Next one.
Next one, we're going to go second trace 0. Left bound, we'll say 2,
4 maybe.
4, 1, 2, 3, 4, and I guess at 3. And so the other one is x equals, 3.5, did you see what
4, I think.
A 4, we think. Okay. So there are x values.
So what does that mean?
Well, this is what is going to make this box have a maximum or a minimum volume. And if we look over here, let's talk about, this is my x cut here. If I just look at this, it looks like the maximum is going to be like 1 point something. Well, what's that 3 talking about? If we look at 3.54, here's my x that's getting larger. And now it is, it's over 3.67. It crossed down here, which doesn't make any sense to have a negative volume. So that 3.5 must have been a minimum.
Yeah, so even though that minimum exists,
it doesn't seem to make much sense.
Yeah.
Because if this distance here is 6, I can't cut out 3.5 from one side and 3.5 from the other side, because that's more than 6. So the domain of this volume function really is up to 3, from 0 to 3.
Yep.
So that means I can ignore this value.
Okay.
And so so my maximum volume, well, if I want to find the maximum volume, I plug in V, or X into V, 1.31. And let's get, do we have the, I wish I would have.
We could do trace in 1.31, right?
Oh, right. Because I was hoping to get the next decimal so that we could make sure the final answer was good to three significant figures.
Best.
But since we lost it, let's just ignore that for now. So I get 4, 1.31 cubed, minus 28, 1.31 squared, plus 48. Oh, my handwriting is atrocious today.
No, it's not.
Okay, and so we're going to do that calculation. Now we definitely need help with that.
Okay, you just hit trace and then...
That's the derivative that we have in here.
Oh, that's a derivative.
So 4 times 1.31 to the power of 3 minus 28 times 1.31 to the power of 2 plus 48 times 1.31 equals, so my maximum volume is 23.82. So max volume, oh, my pen is doing funny things, is, what did I just say? 3.82, 23.8, the 3 decimal places, and this is centimeters cubed. Don't lose your unit point.
So the dimensions of the box?
So
I
now
think that's what it originally had asked.
Right, so the length is going to be 8 minus 2 times 1.31. The width will be 6 minus 2, 1.31. And the height is just the 1.31 centimeters. This one you should find, centimeters. And that one you can do as well, centimeters. I think we've answered everything.
All right, that's it for now.